Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the third part of the Cascode Amplifier. And this is going to be a continuation of a three-part series where we talked about part one, and we've had part two already talked about. I'm going to recap some of these parts in this video, but please make sure to go check those videos out if you haven't already, because towards the end of this video, part three, I'm going to be referring to things I've already talked about in these two parts. So in terms of the progression of the Cascode Amplifier, this is what I consider the fourth progression, okay? Where the first progression is you have a regular amplifier, right? RD, VDD, and you have a V input, an AC signal, and you take the V out. This is what I consider the common source amplifier, and I've done a video on this. The second progression is going to be this common source. So this is V in, this is V out, this is RD, VDD, and we attach an RS at the bottom here. And this is what we consider a common source with source degeneration. Again, I've done a video on this, link in the description below. And again, the reason why we want to consider the second progression is because our AV gain, which is minus the transconductance times R out, this R out is bigger than in progression 2 than in progression 1. As a result, the AV gain is higher. The third progression that we want to consider is we want to eliminate this RS, and we want to create what's called a cascode system. So it's two transistors built on top of each other. So this is R out or V out. This is RD. This is VDD. This is V in. And this is what we consider V bias. Again, this V bias is inputted into this M2 transistor in order to keep it in saturation, because we need both M2 and M1 to be in saturation to draw an ideal current source. As a result, we found out that the AV gain minus GM R out is higher than this AV gain. So this guy is higher. And lastly, the fourth progression, which we'll be talking about in part 3 of this video, of this lecture series, is located here, where, again, you see the cascode below the V output. And these are NMOSs in saturation. And we've replaced this RD resistor with a PMOS cascode, right, in saturation. So this is the answer to the end of part 2. It was in order to have this be an ideal current source, we want the PMOSs to be in saturation. Okay? So the small signal of this fourth progression is shown right here to the right, where we're doing the AC analysis of this. Okay? And the goal, again, kind of piggybacking off part 1 and part 2, is to find the transconductance GM and the R out, or the output resistance, multiply them together and then negate it. And this is going to give us our AV gain, or this is V out over V in. Again, this was proven in the previous parts of this lecture series. Okay, so without further ado, we're going to go ahead and solve for GM, and we're going to solve for V out. Before we do that, actually, though, I want to talk about why a cascode amplifier is important. This is simply a recap from part one. And it says here that a cascode amplifier has a higher output resistance, okay, when compared to a regular amplifier, such as a common source or a common source with source degeneration, leading to a more ideal current source. And the second point is, due to a higher output resistance, we get a higher gain than a regular amplifier, right? So essentially, AV is equals to minus GM R out. So if this goes up, this also goes up, right? So that is the idea of the importance of the cascode amplifier, why we need it or why we use it. So similar to the previous parts, we want to find GM, and we know GM, which is the transconductance, which is again which is I out over V in when V out is equals to 0. So what we can do to our small signal located to the left here is say that V out goes to ground, and we input what's called an I out here. These bias voltages all go to ground because since we're dealing in AC, a battery source is looked as a short circuit. So this is short circuited to ground, right? This here is also short circuited to ground. This is also short circuited to ground. But this VIN, since it's an AC signal, is not short circuited to ground. Okay, so I out over V in when V out is equals to 0. And what we're going to notice here is that, okay, this VGS4 is equals to 0. So this voltage controlled current source here is also equals to 0. This is equals to 0. So this is equals to 0. This is equals to 0. So this is equals to 0. So we can redraw this, right, as this is grounded. Let me fix this up. This is RO4. This is RO3. This is RO2. This is RO1. This is a voltage controlled current source, call it GMVin, simply because this VGS is equals to Vin, because it's in parallel with this Vin. So this here is just GM1 VGS1. So let me go ahead and put the 1 there, or VGM1 Vin, right? So GM1 Vin, and this is connected to ground. As a result of that, we have this grounded. This is I out. Let me use red to keep it consistent. I out. So this is 0 volts, and this is 0 volts. So the current through here, let me call this I PMOS, is equals to 0 minus 0 over RO4 plus RO3, which is simply equals to 0. Okay. So that means no current is going to flow through here. So my I out is going to flow through here. So it's going to flow through this voltage controlled current source, and it's also going to flow through this RO1 value. Let me call this IO1. So then I out, we can say, is equals to GM1 times Vn plus IO, let me call this IO1. As a result of this, if we consider that RO1 is very big, all right, so that means this IO1 is extremely close to 0 because no current is going to flow through here, then that means that I out is approximately GM1 Vn. As a result, GM1 is equals to I out over V in, which this is my equation for my transconductance GM. So again, GM in this case, let me write it on the top, is equals to GM1. So I hope this makes sense. Again, we've done this in the past, but if this is a good refresher, if you have any questions, please post them down in the comment section below, and I'll be sure to get to you. All right, so for the next part of the video, we want to figure out what R out, again, this is also called R Thevenin, is, which R Thevenin, or the output resistance, tells us to say what is V out over V in, V out over I out, given that V in is equals to 0. Again, we've done this in the past, but what we can say here is, let's go ahead and short circuit this to 0. Okay. And this is a bias voltage, so this VB4 is also short circuited to 0. So this is short circuited. So these are the special ones. All right, and we'll deal with those in a little bit. Let me go ahead and apply a current here, I out, and take a voltage source here, V out. Okay. And we've proven this in the past, but because this VB3 is embedded into this transistor M4, it doesn't necessarily send this VGS3 to 0, like our transconductance case. All right. So what this actually equates to is the PMOS becomes, this is RO4, a common source with source degeneration, where RO4 is my degenerated resistance. So this is RO3. This is GM3V. Let me clear some room, make some space here. This is GM3VGS3. And this is V out. As a result, the bottom, or the NMOS, also becomes RO2. This here is GM2VGS2. And this is RO1, and it's going to ground. So, and you might hear this a lot. So let me apply a current I out. This I out is based on the resistance when I look down this way. Let me call this RN. And when I look up this way, let me call this RP. So in short, it's going to be a long equation. So R out is actually going to be this RN in parallel with RP. And what we can say is that RN, based on my common source with source degeneration equation, is going to be 1 plus GM2 RO2. So this GM, this RO2, multiplied by the source degenerated resistance, RO1, plus RO2. And this is in parallel, again, with 1 plus, I'm going to look up this RP, tells me that this is GM3 RO2, RO3, RO4 plus RO3. And again, this equation, this RN and RP equation, are pretty complex to prove, but I have proven these in both part 1 and in the common source with source degeneration video. So please make sure to check that out. So this makes sense. But again, this is the complete equation for RN and RP, and this is your R out. So let's go ahead and write out the full equation for AV gain. So it's going to be a long one. It's going to be AV, which is equals to minus GM R out, is simply equals to GM1, right, which we solved from above. And we have this 1 plus GM2 RO2 RO1 plus RO2 in parallel with 1 plus GM3 RO3 RO4 plus RO3. All right. And this is your complete equation. But let's go ahead and try and simplify this. All right. So we can say then that this is GM1. Let me go ahead and say that this comes out of here because this one is negligible and this RO2 is negligible compared to this term. So this is GM2 RO2 RO1 in parallel with GM3 RO3 RO4. So then that becomes, this is equals to GM1. So I'm going to multiply, so GM2 RO2 RO1 times GM3 RO3 RO4 over this GM2 RO2 RO1 plus GM3 RO3 RO4. So this is an estimation simply because of the work we did here and here. But essentially, you can see that this is my AV gain, and it's a lot higher or bigger than a simple AV gain of, I forgot to put the minus. So this is a minus here, here, and here. But AV gain of a common source is simply minus GM1 RD. As you can, if you do the math, if you plug in some values for GM1, GM2, and all your R's, this is going to be bigger. So I'll put a greater than sign here. Or to be completely transparent, AV cascode is greater than AV common source. Okay, if you found this video helpful, please give it a thumbs up. If you like the content that I'm providing, please share my YouTube channel to your fellow classmates and colleagues. Please leave any questions you have in the comment section below and subscribe to my YouTube channel. Thank you.